So this section is more like the end of grade 11 chemistry, where we are going to mathematically or quantitatively analyze chemical reactions. So last year we did in Unit 3 moles, just straight up, and practiced stoichiometry. Then we did applying the mole concept to solutions and concentration. Then we did, the last unit was applying it to gases. So now essentially we're going to apply quantities to, in this unit we're going to do energy, and then the next unit we will do rates of reaction. Okay, so how fast a reaction goes. So we will calculate moles and look at how much energy is produced per mole, that kind of thing. So when you do these problems, the math problems, a lot of them are going to be calculating similar quantities, but different ways. So we will look at, today we'll just look at what happens when there is a temperature change, or Q. So sometimes in physics, they get to Q equals mc delta T. So that's one of the simple calculations we'll do. Then we'll look at what happens when energy is transferred. And we will do 3 labs with a similar procedure. And then when we get to the end, or the 3rd lab, that is the next option for a formal lab. And by the time we get to the 3rd lab, which is called Hess's Law, I have students who get like 0.6% error. So you're just going to get better and better and better. And there's not many things in, or not everything in science gets the designation law, because a lot of it is still very theoretical. The energy concepts, we're going to talk about the law of thermodynamics. So even in our simple lab, we're actually going to use coffee cups, styrofoam coffee cups as our insulator. You still get the law holding. So it is very easy to prove how changes in energy the laws are held. And we as humans exploit these laws all the time. You plug in a lamp and the lamp converts the electrical energy into light energy. There is sound energy. There is energy we get from food or calories or joules. So all kinds of types of energy. So when you see the word dynamic in science, then it often means things are happening. So we're going to talk later on about, in the 2 units from now, called dynamic equilibrium, that there's always changes happening in reactions. So energy transfer is, essentially makes the world go round. We have turbines that are powered often in Ontario by steam and the hydroelectricity. So those turning turbines then provide the energy, convert the energy and provide it to the power grid so that we can, turn on the lights, etc. Okay? Today we'll look at the general terms that we need for this unit, and we'll look at the differences between physical changes, chemical reactions, and nuclear changes in terms of their energy requirements, or how much energy they give off. Okay? So physical changes are going to have the least amount of energy. So things like melting, boiling, and dissolving are all considered to be physical changes. Sometimes when we get to evaporation, people will say, okay, but don't you have to have 100 degrees Celsius to get something to change to a gas? Remember, water has very special, strong intermolecular forces. I know we think of boiling as hot, but changing to a gas doesn't necessarily require a ton of energy. Then chemical changes. So we'll do dissolving, we'll do a physical change, and then we'll do neutralization, which gives off a characteristic amount of energy. And then when we get to the Hess Law lab, it'll be kind of our limit of the coffee cups and how much can be contained. You could, if you move on and get to, 2nd or 3rd year and you're still taking chemistry courses, you might get to labs that have metal containers for the experiments to be completed in. And then you could even do things like burn substances and see how much energy is given off. Okay? And then nuclear changes technically are not like chemical reactions at all. You're actually changing the nuclei. All of these reactions or changes give off energy, and you could blow up cities. You can, again, power the power grid. We have in Ontario, we have 2 nuclear power plants. The US has 109, like they have tons of nuclear energy. So obviously the amount of energy given off is enormous. The sun is powered by nuclear fusion. Okay? So I just want to make sure, and some of you will have taken physics, and these definitions, like you would go way beyond what we need for chemistry, but just so we know the difference between potential and kinetic. So potential energy, the official definition is the energy due to the position. So in physics, you talk a lot about parabolic motion, or like dropping something or throwing something. We're obviously not going to throw chemicals around. So ours is more about the composition. How much energy is stored in the chemical bonds, or how much energy is required to break those chemical bonds. That's what we're going to kind of do. So another, again, sort of physics-focused definition is can be used to do work. So something like, winding an elastic, or your mousetrap car, and then it makes the mousetrap car go. So we are going to do, the work we're going to do is chemical reactions, okay? Or even inside your body, biochemical reactions, eating the food that you choose to eat, which is broken down into glucose, and then those bonds are broken and the work is inside your body, okay? So chemical bonds are a great source of potential energy. And when you have chemical changes or physical changes, the energy can be absorbed or released. So we'll look at a bunch of different ways to tell which is which. And some of it will be, we just haven't talked about things like this before. So we have talked about, so we just did organic. If you have an alcohol, how much energy is required to get those molecules apart? We didn't really think about then, is that going to make a certain type of reaction? One of my grade 12 biology students, who's in this class as well, or in the next period, she was asking me about, endergonic and exergonic. So those kinds of ideas apply to chemical reactions not inside the body as well, okay? And so then kinetic energy is the energy of motion. So what we can't do, unfortunately, is stick a thermometer in between the bonds, in between 2 atoms, and decide how much energy there is in there. But what we can do is put the reacting system inside of something else. Commonly, we're going to use distilled water, and then the distilled water, you can easily measure the temperature. And again, because of the law of conservation of energy, then the energy transferred should be equal to what was absorbed or released. Okay? So the technical definition of kinetic energy is the energy of motion. So what we're going to do is the thermometer is an average measure of, not thermometer, temperature is an average measure of motion of the kinetic energy. And so we can use, even our not great thermometers will still help us get good results, okay? So we are going to measure how potential energy is transformed into kinetic energy, or vice versa. How is kinetic energy being transformed into breaking bonds? So one of the homework questions talks about trying to decide which is greater, the potential energy of something or the kinetic energy. I debated whether I should include that question in the homework because sometimes the wording of things is tricky, but what you're looking for is something happening. So kinetic energy is more like a verb kind of tense, like something is happening right now. And potential energy, you're going to look for words like stored or can do and stuff like that. Give it a try. Okay, so another term that we sort of use all the time. And again, it's tricky because we think of heat as warm, but there are situations where energy can be changed at really low temperatures or transferred at really low temperatures. So a lot of times you'll see in the question the words thermal energy, and it's essentially just measuring what is the energy in a substance, and then how is that energy being transferred. So the law of conservation of energy states that the energy of the universe, I don't know if yours is cut off too, that was weird, of the universe is constant. Wouldn't it be great if we could have perpetual motion machines and create energy from nothing? I think our lives would be a lot different, but that is not possible. So the change in the energy of the universe is zero. So this symbol means change. So when we do a lot of our calculations, we're going to look for the change in the energy of something. So you'll see that symbol quite a bit. So the change in the energy of the universe is zero. You can't, whatever was here has always been here and always will be here. It can be tricky because you might have energy lost. So when I was a kid, we had these light bulbs called incandescent. So when you plugged your lamp in, these incandescent light bulbs lit up, great, but they got so hot that if you touch them, instantly burned. They were releasing so much waste energy as heat. When you eat a substance and then you go for a run and it's winter time, then, usually your caregiver says, put a hat on, you lose energy through your head or something like that. But it is sort of true. We get sweaty. That's waste energy we're wasting from the food that we eat. So it's yes, energy is transferred, but it can be difficult if you have an open system to actually get an accurate measurement. So we are going to try to be closed. So when you are working with your partner, you want to be a good lab partner. You have your vessel, and you can't measure the temperature, measure the solid or whatever, put them together, and then just be standing there being like, oh, hey, what are you having for lunch? You have to close the lid ASAP. It's very sad if it knocks over, somebody spills it, because essentially you have to start again, and everybody's like, oh, you spilled. And it's not a big deal. However, we are really going to try to minimize the interaction with the environment, which is our classroom. Okay, so you put a hat on your head to try to minimize, it's like an insulator, keep the heat inside your body when it's winter and it's cold. So the transfer of energy from one substance to another is called the first law of thermodynamics or thermochemistry. And there are all kinds of laws, Newton's laws of motion. For every reaction, there's an opposite but equal reaction. I saw this really cool video, and this woman was standing on, it looked like one of the carts we have, and she had rollerblades on in the hallway. So it looked like a teacher. She's standing on the cart in her rollerblades, and somebody is pushing the cart, and she isn't moving. So there's lots of cool experiments, cool ways to prove the laws of energy transfer, the laws of motion. So if you're interested in that, that is part of physics and part of chemistry too. So when we look at energy transfer, one of the ways that we are going to measure this energy change is using the system. Oh, not yet. So system and surroundings, but we'll talk about this first. So when you have heat or a measurement of heat, or you could call it thermal energy, then we are looking for how is the energy being transferred. We will use metric units, And so our units will be in joules and kilojoules. If you are an external video watcher and your video happens to be American, then they might talk about calories and kilocalories. It's the same thing, just when you have the metric system, it's easily converted between values. So if you have joules and you want to get kilojoules, you divide by 1,000 and then the reverse. If you have kilojoules and you want joules, multiply. Same thing with kilograms and grams. Joules and grams are considered the base SI unit. When you have heat, then if something is hot, it's going to transfer spontaneously to a cooler object. And again, even though maybe you've never considered this before, if you have a pot that you use to cook with and it doesn't have a rubber handle and you put your hand on the metal handle, then the heat transfers into your hand. That's a spontaneous thing. And then temperature. So we use little q or lowercase q and then capital T. The Q, it doesn't, to be honest, if you use capital Q, that's not a big deal. But T, we're going to use temperature as capital T in this unit. And then next unit, we're going to do time, which is little t. So try to use capital T for temperature as much as you can. So this is a measure of the average kinetic energy. So when we use the thermometer, it is an average. So let's say, again, you have a boiling pot of water. There's obviously water really close to the element. There's obviously, because it's not usually a closed system, then the steam is moving quickly and escapes the pot. So the temperature at different spots in the pot will be different. So same with us. When you use the coffee cup, they're not that big, but you do kind of have to gently stir and keep everything moving so that your average is as average as possible. Okay, but like I said, by the end, when you get to the formal lab possibility, we get really, really good results. Okay, because we are a simple lab, we're going to do degrees Celsius. We do not have thermometers that measure in Kelvin. Again, if you continue with chemistry, you might do conversions or have different equipment, but we're going to stick with this, degrees Celsius. So again, if you're watching an American video, then they would use Fahrenheit. When I was in high school, we used to do the conversion of joules and kilocalories, which is multiplying by 4.28 or something ridiculous. And it's just, we kind of even moved away from that. So, you know, I feel like the metric system is becoming the system of science. So you might find that if the video is newer, they use joules and kilojoules too, which is better. Good. There we go. Okay. So we are going to often put our system in some kind of surroundings so that it's easier to measure quantities. So when you have a system, that's what we are studying or observing. So in a chemical reaction, it would be the reacting particles. For physical, you could do any physical change. We're going to do dissolving solids. And you can do all kinds of experiments. When I was in high school, we had to watch and measure the temperature change as an ice cube melts. So yeah, it was real exciting. Okay, so we're going to do one that's a little bit faster. And when you have if if you're ever hurt and you have to get a hot pack or a cold pack and you like crack them and they mix together, that's essentially thermochemistry. You're either making an exothermic reaction where it gets warmer or an endothermic reaction where it gets colder. So we'll do one that's kind of got a useful application as well, okay? And then the surroundings are outside the system. So when I was a student, they always said never use the word in the definition, but you could literally say surroundings surround the system, or if you prefer the other version, you could say the surroundings contain the system. So the system has to be fully surrounded by the surroundings, okay? So how are we going to make sure that happens? Like I said, you're going to continuously sort of gently stir. This is bad handwriting. Let me just fix this. And the environment is outside the surroundings, and we're really hoping to actually not interact much with the environment, okay? Because the measurements are just harder to take. We're not going to walk around with a thermometer in the classroom. Oh, the temperature is this here. Oh, it's this over here. Probably right now you can feel the air moving. If you're sitting underneath a vent, the temperature could be different than in the middle where there isn't any. So we want to minimize interaction with the environment. Okay, so we are going to try to switch from doing open system reactions. That's mostly what we've been doing up until now. And because we don't really care, we're not really measuring exactly how much energy is being absorbed or released by the system reacting. In this unit, we're going to do closed system experiments. So for example, once you start an experiment and your lid is on, then opening it to see if, the stuff's dissolved or whatever is going to be bad. Can't do that. So that's why we're, continuously gently stirring, and then do your best. It is what it is. Okay? But like I said, if you're a good lab partner and as soon as you put the lid on, you're good to go and you're keeping it as closed as possible, you should get really good results. So people like that. Okay, so when we have a reaction, breaking bonds and creating bonds is always what happens. And breaking bonds requires energy. And creating bonds always releases energy. So we have to look at the change in energy or see what the net change is. Which of these is greater? Is the requirement of energy greater, or is the release of energy greater? Not always. Sometimes one of them is greater than the other. So, for example, combustion reactions, we don't necessarily, like you wouldn't put magnesium metal inside your gas tank and burn it. Yes, you could do that, but when you burn gasoline, so many carbons, the potential energy in those bonds is so much greater. So then you get such a greater release of energy that then that's a much more useful combustion reaction. Or the same thing, if you want to bomb a country, you're not going to throw some magnesium on them. You're going to use a substance that has a nuclear change because the amount of energy released is insanely greater. So actually, that's a good question because that's essentially what we're going to do. We're going to look for all of grade 12. We're looking now at reactions in a different way. So for example, when we get to equilibrium, we're going to talk about how some reactions, actually once you start making the products, then the products start to re-react and then the reactants get formed again. There's actually a lot of reversibility in reactions, which we've never told you about before. So we're just analyzing reactions that we have told you about, you've labeled, you've balanced, whatever. Now we're looking at, okay, really what's going on. And I was saying this to my grade 11 students yesterday. We don't really talk to you a lot in grade 9 and 10 about conditions for the reaction. So if you think about when you go to do labs in grade 9 and 10, you probably got there and there was a little beaker with a liquid inside and a pipette. Most of those are actually aqueous solutions. Why do we use aqueous solutions? So the ions are available to be displaced. But we don't really tell you that because, you're kind of just in the beginning, the fundamentals of chemistry. So we're going to look more into why do we use combustion reactions to heat our homes and power our cars? Why don't we use burning metals? Because there's just not enough energy released. So if you've ever thought to yourself, why, if climate change is such a big deal, why do they continuously keep burning fossil fuels? We've known for a long time that this was not a good idea. It's because the amount of energy released from those bonds is hard to efficiently replace. Which you might say, well, that, isn't the Earth hard to replace? Yes, right? So there's the conundrum. So this is going to be an important concept every time we do a lesson. Unfortunately, it is the same word as biology. Mr. Adams, Ms. Coulin, they say endergonic and exergonic. It's the same thing. So if a reaction requires more energy to go, or the absorption is greater, that's called endothermic. If you have a release of energy, that's called exothermic. So I think of it like exiting, like heat is exiting the reaction, then it's exothermic. So when you are given, one of the questions in the homework asks you to look at a situation in words and think about whether energy is released or absorbed. And some of them, again, are reactions you would have looked at before, we just haven't considered the release of energy. So gasoline burning inside a car. Burning or combustion is an exothermic reaction because the energy is released, and then that energy released, powers the pistons and makes the wheels turn and the car goes. Okay? And we're going to talk about these terms over and over and over and over again. Okay, so these, if you have the note printed off, there are two charts. We're going to describe the difference between endo and exothermic. So I'm going to do, the first one we'll do endothermic. It doesn't really matter. I went in order that they're listed here. Okay, so for so when you have, in both cases, always, 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 reactants have to have bonds broken. Whoa, sorry. which requires energy, or if you prefer the word absorbed energy, same difference. And then when you have products, the bonds have to be formed. Bonds are formed in products, and energy is going to be released. Okay, so we'll do endothermic first, which means that the system or the process, the reaction, has to absorb energy to get the reaction to go. So the energy absorbed is greater than the energy released. If you're not a fan of the alligators, you can write greater than. So energy could be absorbed from water. It could be absorbed from an electric current. It could be absorbed from, what else could you do? Even moving parts. So there's all kinds of things that can provide the energy depending on what the situation is. If the air was warm enough and the requirements for the reaction weren't that great, you could even absorb energy from the air. So really, in your lab past, anytime we have to use Bunsen burners, so let's say you need to make a hot water bath. So you need that water to get warmer. Maybe you want it to go all the way to boiling. Then, so that is a process that requires energy. You have to heat it up in order for the evaporation to occur. So we're going to do almost the same thing. So we're going to write bonds broken, bonds formed, energy absorbed, energy released. But now the energy released is greater than the energy absorbed. Okay, so energy is exiting the system. If that's not your thing to think of cutesy little analogies, then don't worry about it. You don't have to think of it that way. Okay, so when you have temperature change, so that's easy to measure with a thermometer, then you can calculate the thermal energy transfer, the heat transfer. But when you don't, and you are really trying to consider what's happening in the system, then we have to look at other variables or other situations, other ways to calculate our data. So we're going to talk about something called enthalpy. And the reason we can't just say heat is because that doesn't really give us all of the ideas behind what's happening in a chemical bond. So the total internal energy is called or is measured by enthalpy. So we've talked about before some reactions are more vigorous than others based on the size of the atom, how many electrons it has to lose, even conditions that are described by the physical state. So a solid is less chaotic than a aqueous solution, dissolved ions, or a gas. So there are conditions in a chemical reaction that you can't measure. You can't put your thermometer in between the ions when they're dissolving. So we have to look at a different way to measure the enthalpy. So in order to take into account all of the conditions, the trends or the properties, chemical properties of a substance, how much entropy or chaos is in the reaction, we're going to use enthalpy. So today and tomorrow, when we do a situation where you can measure delta T, then we'll calculate Q. When we get to later on in the unit and we look at reference values using bond energy values, enthalpies of formation, measurements of the actual composition of a compound, we'll talk more about delta H. Okay? So when you have physical changes, like I said, we're going to do dissolving. But you could do other ones as well. You could do evaporation, condensation, melting, etc. Melting, freezing, all of those either require a certain amount of energy or release energy. But because you're breaking the intermolecular bonds, the delta H values are small. And so when you have an enthalpy change, then the units can be considered for how much energy would you get per mole. So we'll do that tomorrow as well. So even though the questions themselves are actually very, very different in thermochemistry, there's also quite a few formulas. And sometimes students will say, well, how do I know? What do I do? So the next slide is just a really quick sketch of a graph that you can use to help you visualize what's going on. And I fully just made this graph up. Okay, this is not a real graph. But what happens is you can measure temperature easily. But if you, let's say I made you watch an ice cube melt and measure the temperature changes, what you would notice is as you went along, as you had your ice cube changing states, then there would be situations where, oh, sorry, this is temperature, where the temperature is changing and the temperature is not changing. So that we're going to do, those are the two formulas we're going to do first. So the slanted line means particles are moving faster. Therefore, you would have a delta T value. And then where the plateaus are occurring means that the energy is being used to actually break the intermolecular forces. So one of the differences mathematically in the formulas we're going to use, one of them will have a delta T and one of them will not. If you don't like the word plateau, it's just a fancy way of saying the flat lines. So we're still adding energy, but the temperature over a period of time would not be changing. Okay, and then chemical changes, and we'll talk a little bit about nuclear changes, but we are obviously not going to do nuclear changes in our classroom, so we'll focus more on physical and chemical as the unit goes along. So examples of chemical reactions we're going to do single displacement in our calorimeters. We're going to do neutralization, which is technically double displacement. Many of the questions when we get to the reference or theoretical values will be combustion. We are not going to burn things in coffee cups, but if you had a better vessel, you could. So when you have a chemical reaction, you're going to get more energy because the chemical bonds between atoms, so these are intramolecular and the physical were intermolecular. So the definition of intramolecular is between atoms. Those are stronger automatically than intermolecular, and the stronger a bond, the more energy you need. And then nuclear changes, you're actually changing the nuclei. So there is fusion, which is smashing nuclei together, and fission, which is decay. Either way, you're going to get a significant release of energy. Einstein's famous, one of Einstein's famous equations, E equals mc squared. So you have the speed of light and mass and the energy produced by these transformations. Which, again, obviously, way too much for our classroom. And even if you want to read a little bit more, there is more in the textbook. You can actually, you write a nuclear reaction with the standard atomic notation like this. Okay, where the mass, it goes in the top and the atomic number goes in the bottom. And the way that you balance these is actually to make the mass numbers add up to whatever else is being added or decayed, and the atomic numbers add up. So you don't even balance them the same way. They are not like chemical reactions. Okay, so today we will do the first simple calculation. I don't know why the formula didn't print, but that's okay. So we're going to look at the change in thermal energy or the change in heat. So this time in this formula, you have to have a delta T. And when we do delta T, it must be TF minus TI, or T initial minus T final, or T2 minus T1. And eventually, when we get to more complicated questions, the sign, whether it's positive or negative, is going to impact what our data and how we analyze it. So you have to do T2 minus T1, okay? The Q will be in joules usually because the specific heat capacity, I'm just going to switch for 2 seconds. The units for heat capacity given in your textbook are joules per gram degree Celsius. So that means the Q has to be joules, the mass has to be grams, and degree Celsius is degree Celsius. Okay? So this textbook is a little bit better. The old version always made you look up the reference values. Sometimes it's in the question, but sometimes you have to look it up. We talked a little bit about heat capacity in grade 11 when we talked about water. Water has a high heat capacity because it takes a lot of energy to raise the temperature of a gram of water by 1 degree Celsius compared to a metal, which would have a very low heat capacity. We talked about it in the water section because we talked about how, like lake effect snow, it takes a long time for a giant lake of water to cool down in the winter and warm up in the summer because of its heat capacity. So we're going to do the most difficult of these kinds of questions because it's all multiplying. It's very straightforward. However, if you get a question like this, depending on your math prowess, you can solve for delta T and then solve and then rearrange the adding and subtracting one afterwards. So that's what I'm going to do. You could do it all as one step, but then you would have to make sure you're distributing, and so it's up to you. Okay? So a sample of ethylene glycol used in car radiators has a mass of 34.8 grams. When you do these questions, you just have to check. So our heat capacity is given in grams, so that's good. Later on, we will get to situations where it's kilojoules. So you just, again, have to read the question carefully. It gives off 783 joules. And then it says the initial temperature is 22.1. So I don't want to mess things up, so I'm going to do delta T first. What you can do, and you know what, even if you do it here, you can sort of cross things out and see, actually you can't cross that out, cross things out and see what you're left with. You can put units in your calculations and do dimensional analysis. Again, sort of like what you would do in physics. Whatever you choose, it doesn't matter to me, but you have to make sure your answer has the correct units. Okay, so joules will cancel and grams will cancel. Again, you can decide, I need to multiply these first before I divide them, this by them. I have a good relationship with my calculator. I know how to make it have brackets, because when you do this, when you do these calculations and you isolate delta t, that's our x value, like the unknown, then you have to make sure you multiply first before you do 783 divided by that. If you like to write out and show your inverse operations, you can. If you're sort of beyond that and you don't want to, that's fine. You could even write it like this. Whatever. So you should get 24.43 degrees Celsius. And then we'll solve for TF. Okay, so when you do these questions, you just have to follow the algebra rules, right? Bring this to the other side. So again, if you're used to writing it out, okay, and then doing the math, that's great. If you want to take shortcuts, that's fine too. But often this whole unit is really well done. So the more you get good marks here, the better, you can help your mark. Also, when you get an answer, often in this unit, you can kind of think about what your answer is and read the question and make sure and see if it makes sense. So it says in the second sentence that the sample liberates energy. So then the final temperature should be higher than the initial. It's gotten warmer, okay? So you can check that as well. So if you were not an organic chemistry lover, this is much more logical, usually, a well-liked unit. It's very straightforward. So, but there is a bunch of problems, different kinds of word problems. So what we're going to do is 3 quizzes. And the 3 quizzes will be out of like 15 marks. And I'll take your best 2 out of 3. So the first quiz isn't until next Wednesday. I'll give you a practice quiz, okay? So that you don't get to the unit test and all of the word problems kind of run together, okay? So the homework itself doesn't take too long. The only thing is that if you had, say you had this as your answer, your textbook would round this to 47. So if you check the answer and it's a little bit off, then maybe take a look at the solutions if you want to know the exact number, because they do like to round. Okay?